Okay, so we've got a vector field, we've got a surface. We want to compute flux. Drawing the surface, as you've observed, is going to be the first question here. And let's see here. So we're looking at that equation. Let me solve for y. I see that y is equal to 5 minus x squared minus z to the fourth. And there's a couple of different ways you can do this. One thing you could do is start looking at cross sections, right? And so, for example, if you set x equal to a constant, you've got sort of upside down. They're not parabolas, but because they're quartics, right? But they're kind of like parabolas, right? You could set z equal to constants, and you get stuff that's again sort of upside down. Well, parabolas in this case, but in both cases, y is sort of it's curving what I'm going to call in the downward y direction. In other words, it's curving as in the direction where y decreases because of these minus signs. And so this is not going to be a good picture, but it's an approximate picture. It looks kind of sort of like this, where that's 5. So, we'd like to be able to use the rotation point of view. It just doesn't work here because it's just not it doesn't fit the proper form, but it's not that far off. And that's another thing you could do is you could say, you know what, this looks approximately like what it would if that was a squared, and then you could draw the rotation and you get something that looks a lot like this, and you say, well, this is going to be kind of different, but it's going to be, z is going to be decreased, y is going to be decreasing faster with z in this case, and so you would just maybe qualitatively change it a little bit.
So it have a similar shape.
Yeah.
So you could still find the right balance.
Yeah, it's still pretty close. Yeah, that's right. That's right. But ignore, and that's just an approximation. But one thing you certainly can do is look at different cross sections. Yeah, does that make sense?
So set y equal to constant and see how it changes if you move along our axis.
Yeah, that's one thing you can set. You can set all three of the variables to equal to constants at different times and see what the cross sections in different directions look like. It's kind of easiest, I think, if you set x equal to a constant. And then you get a constant minus z to the fourth. Or if you set z equal to a constant, then you get, again, constant minus and then x squared, and you get these kind of parabola-looking things in the backwards y direction. Anyway, it's just different points of view on it. So having this picture drawn, again, you take the vector field, compute the divergence of it, just for good measure. Because whenever you're computing flux, go ahead and compute the divergence. And, let's see here. I hope this works out. The x partial is negative 2x plus 3y squared. The y partial is 2x minus 3y squared. Oh, that's cool. And the z partial is 0. So good news, it is 0. This is surface independent. I can change this surface. All I have to do is make sure not to change the boundary curve. Right. That make sense? Let's think about orientations. This surface was oriented in the positive y direction, so like that. That means that this curve is oriented like that, which means that when I choose the new surface, and I'm going to choose that one, well, let's see, I better orient it that way in order for the orientation on the boundary to be the same. Right? Does that make sense? Okay. So now you've got a new oriented surface. Notice on that new oriented surface, I didn't draw that very well, did I? Let's see, I needed one. That new surface was supposed to be in the XZ plane. I drew that poorly. Here, let me fix that. just kind of ignore that. We'll just kind of ignore that. Okay, there we go. That is in the XZ plane now. And y is equal to 0 in there. So our vector field is going to simplify somewhat, because y is equal to 0, and let's see, the vector field becomes z minus x squared 0, 0. Well, that simplified nicely, right? Our unit normal vector, this new capital N unit normal vector is 0, 1, 0. And that's dot product is 0, flux is 0.
And then the equation for the surface. How do we know the radius?
Well, it turns out you don't need to, right? Because we know that we already know that when we're computing the flux through this disk, that we're doing a double integral of f dot n ds,
Yeah.
and we already know this dot product. Oh, sorry, this dot product is definitely 0. So the details of the shape of the disk end up kind of not mattering. Yeah, does that make sense? Yeah. But if you did want to know, if you did need, let's say, to know, then the point is this disk is where, well, the boundary is this curve where the equation happens and where y is equal to 0. So the equation would be x squared plus z to the 4th equals 5. And that would be an annoying double integral to do because you've got 4th powers, or worst 4th roots conceivably. But as it turns out, don't need to know it. And it'd be doable, right? Even if we did have to deal with that, it would just be sort of inconvenient. Yeah. Okay.